how is lab 3 going? Any questions, problems? Anyone get it finished already? Anyone? No? Okay, so we have our exam next week too, right? Midterm exam, it's going to be just online. You'll have 75 minutes to take it. Once you start it, you can take it once, multiple choice, open book, open internet. It'll cover everything that we've covered up until this point. Does anyone want me to do any kind of review for the exam? Everyone seem pretty comfortable with that material?
Did you do like I²C?
Sure. Yeah, I could talk about that. I'll kind of blow through the first lecture just to make sure everyone's comfortable with this stuff. So we talked about programmed I/O. Everyone okay with that? Okay. So recently we talked about Avalon, and the Avalon bus module would be this interconnect. So this is the thing that actually would translate the address to, and then have it targeted towards a specific peripheral using this on-chip network. This slide, I actually made this picture for the Arduino Atmel chip, the 8-bit Atmel M28P. I don't know what kind of interconnect it uses on chip. I have no idea. Probably maybe something proprietary to Atmel. But most chips use AXI, which is the ARM extensible interface. That's what your phones use. Avalon is, I think, kind of on its way out, but it's a simpler. Avalon's nice because it's a simpler protocol, and it's only used, as far as I know, it's only used in the Altera FPGAs. You can also use AXI with those too. You might have noticed when you create your peripheral, you can actually choose an AXI peripheral. Okay, so we talked about address ranges, and then we talked about bit manipulation. Everyone okay with that? So you have to be able to set bits to 0, set bits to 1, isolate specific bits and bit fields. We talked about and then we talked about pulse width modulation. I think everyone's pretty comfortable with that after lab 2. Interrupts, there's various kinds of interrupts. The question there is whether or not you have some kind of a handshake for the interrupt, or if you just have a straight interrupt going into the CPU. So different technologies deal with this differently. The handshake, though, is a way for the peripheral to know whether the CPU has acknowledged the interrupt and when it's finished processing the interrupt. But it requires two wires. And then we talked about SPI, synchronous, 1 bit at a time. And then we covered exchanges versus transactions. Everyone okay with that? Okay, and then now keep in mind that this protocol that we use for transactions is arbitrary. It's not defined in the protocol. The only thing the protocol defines is the exchange, which is where the master and slave exchange 1 byte. The transaction is kind of a hack on top of that, where you do 1 exchange for the header and then subsequent exchange for the payload, right? And then we got to I²C, and I²C. Oh, we talked about UART first, actually. So UART uses the start bit and the stop bit, and it's generally used. It's slower. And it's asynchronous. So the source, both sides have to have and agree on a clock frequency. The problem is that there's no way for them to agree on a clock phase. That's the problem. That's a big problem. So what ends up happening with UART is that because there's no way for them to lock their phases, only their frequencies, the baud rate is the frequency, the channel frequency, which defines the amount of time each bit is on the channel. Because there's no way to lock in the phase, it's common to have bit errors. I don't know if I should say common, because it's also a very slow channel. So the longer the bit time is, the baud period is, or the lower the baud rate is, the less likely it is you'll get a bit error. But there's no guarantee that you won't get a bit error if the receiver tries to sample the bit at the same time the sender is changing the bit, right? And so that's why they have that parity mechanism in there, which is optional, but the parity allows you to detect certain types of errors. And so in this case, just before the stop bit, you have the parity bit, which can be even or odd, and the even or odd parity just forces the number of 1 bits outside of the start and stop bits to be even or odd. Okay, and then we talked about multi-SPI. So if you want to have, you can never have more than 1 SPI master. That's a limitation. At least I don't know of any way to have more than 1 SPI master. We talked about in Avalon. Avalon, you can have multiple masters. Why is that? It's because of the bus module. Those bus modules or those interconnect modules that are in there that serve as intermediary, that's really what enables there to be multiple masters in Avalon. And in SPI, there's just no way. There's no way to do it. You can have multiple slaves, but even that's tricky. You either have to do multiple slave selects coming out of the master and tri-state the mesos coming back, so only 1 transmits at a time, which is risky because if something happens and 2 slaves try to send data on meso at a time, you can end up in a conflict. Or you can go daisy chain, which is kind of similar to how JTAG works, just a big chain of bits that run through, snakes through everything. So those are your 2 options. SPI, on the other hand, we talked about push-pull and why conflict is bad. SPI uses an approach. I2C. I2C has multi-master, but it uses an approach like Ethernet, where you just kind of, if you want to take mastership of the bus, you kind of just butt in, right, and try to take control of the bus. And if there's a collision, if 2 hosts try to get mastership at the same time, there's some kind of a detection mechanism for that. Ethernet has that, and I2C has that. I don't know what it is. I don't know how that works, actually. I'm kind of interested in that. Like, somehow there's a circuit in there that's going to detect if I try to take mastership as at the same time someone else does. Unclear how that works. But there's a mechanism in there. And in the case of I2C, they use the open drain style where they just have a pull-up resistor, and then if no one sends a bit, the wire is 1. Actually, it's slightly below 1 because there's going to be a voltage drop over that resistor, but a small one. So for a 5 volt and a 10 kilo ohm pull-up, and assuming that the off resistances of all these guys is, well, 1 mega ohm each, so this is 1 mega ohm in parallel. I think typically, though, the off resistance for a CMOS transistor is usually even higher than 1 mega ohm. So, but then again, it also, the more things you put on there, even with a large off resistance, if you hang a bunch of hosts on that bus, then you're going to have a lot of parallel resistors down to ground. So that effective resistance to ground will go down, obviously. So it all depends on what the off resistance is and how many devices you're on there. So this is just a contrived example, but in this case, I had a 4.9 volts, for a 1. So I had a 100 millivolt drop over this pull-up resistor. But again, it all depends on, how everything is hooked up, right? But generally speaking, you want to have a relatively small drop over that pull-up resistor. And then if anyone pulls down, then you can set the bus to 0, right? So the bus is basically, when I say bus, I mean the wire. And when I say wire, I mean each of the 2 wires that are part of I2C. There's a clock and there's a data wire. So for each of those wires, the default value is 1, or someone can pull it down to 0. If 2 try to pull down to 0 at the same time, it won't be catastrophic. Yeah, you'll get a little bit more current because the effective resistance to ground will be lessened because there'll be 2 transistors pulling down in parallel, right? So, but it's designed to not hurt you if you get a collision, right? Does that make sense? So in other words, you got these wires that anyone can take control of, and the protocol is, it uses a start and a stop like UART does, except it's not really a start and stop. So in UART, the start and stop bit are a slot. It's actually a period of time where the period of time is 1 divided by the baud rate. That's the amount of time in seconds. And that's how long the start and stop bits occupy. But in I2C, it doesn't work like that. The start and stop are not really bits, they're signals. And the signals are created by having a situation where the data changes when the clock is high. That's it. If the data changes when the clock is high, that can only mean a start and stop bit, because otherwise you don't change the data when the clock is high. You guys remember that? Okay, so now the transition that happens is different between start and stop. In start, the data is being pulled down when clock is high. And is it the opposite? Yeah, it's the opposite over here. Notice that the data is being pulled up with the clock is high. Right, so the start and stop is changing data when clock is high, but more specifically, pulling down the data when clock is high is the start, pulling up the data when clock is high is the stop. Right? I got that right? Yeah. Make sense? So they're not really bits, they're just like signals, I guess, or events, or situations. I don't know what you call them, start and stop. And then the bits are sent using a latch mechanism where the bits are not they're not sampled on the edge of the clock, or the data bits, I should say. The data bits aren't sampled on the edge of the clock, they're sampled whenever the clock is high. So the data doesn't change when the clock is high, and the clock high meaning that I'm going to let the bit in. Right, so it uses a latch. This is a latch-based. It's very rare to see latch-based systems, level-sensitive clocks. But I2C is an example of that. And then the only other thing that's confusing here is that the master controls the clock the entire time, unless, now there is a caveat there, the slave is allowed to grab hold of the clock and pull it low and keep it low. That's called clock stretching. That's if the slave decides it needs more time to do what the master is asking of it. But generally speaking, the oscillation of the clock is happening, the master is doing that. And then the data signal changes hands during the transaction. So it starts out in the master's hands, then it goes to the slave hands to send the acknowledgement bit, and then if it's a read, it goes back to, or no, if it's a read, it stays in the master's hands, stays in the slave's hands. So the slave acknowledges the address. Actually, it's more than just the address. It's the address plus the read or write flag, right? So if it's a read, the slave will send the acknowledgement and then the data, right? And then the master will take control to acknowledge the data, right? Whereas if it's a write, you have one additional changing of control of data, because the master sends the address, the slave sends the acknowledge, and the master has to then send the data, and then the slave sends the acknowledgement. So there's one additional change of control on the data. Okay? Now this is very similar to the way the CAN bus works. The CAN bus is similar, except CAN is controller area network. It's used in cars. And so the CAN bus, instead of this open driver, the CAN bus actually uses a differential system. There's 2 wires. And so when those 2 wires are shorted, that's a 1 bit. And when the 2 wires have a voltage between them, that's a 0 bit. And then the CAN bus has a little bit more complex packet structure. It has more fields in it. But it works in a similar way. It's multi-master. And CAN is really cool. One of my friends, Austin Downey, his professor in mechanical engineering, he just bought an aftermarket self-driving car module for his Volkswagen. So his Volkswagen doesn't drive by itself, but it has an actuator for the steering wheel and I guess it does this like self-parking or parking assist. And that is controlled by the CAN bus. And there's no security on it. If you can plug into the CAN bus in the car, you just plug in the bus, you can send commands on a specific, which is based on address. So there's just a specific address you send, and then you can tell the steering wheel to turn left or right. You can have the accelerator come on or the brake come on. I'm kind of surprised because you would think like, you'd think that the mafia or someone would put that under someone's car and make them drive off a bridge. But There's no security. But he bought this thing you just mount it on your dashboard, and it has the cameras that face front and back, and it'll just use the CAN bus to control and drive your car for you. It's kind of cool. Of course, the Teslas have that built in, and some Fords and I think Cadillac has that built in. But you can buy aftermarket modules now. It's basically all it is a phone that speaks CAN. Done. Right? You can have the car, you can have it drive your car. So that's kind of cool. But yeah, SPI, I didn't talk a lot about CAN. I might add that later now that it's becoming, I think, a bigger deal. But anyway, then we talked about JTAG, which is just sending bits through. And JTAG uses a state machine to put the JTAG chain into a specific mode. And the mode can be, give me an address or give me your data, basically. And that state, the state changes are controlled by a what's it called? Test mode select. So test mode select is you send a sequence of bits in and you can use that to go into a specific state. And of course, we all use JTAG to program the FPGAs, and in 3.13, we use them for the UART, to print. You might have used it in this class too, to print messages at the console. That all happens over JTAG. Actually, it's weird because on the FPGAs, it uses USB at the lowest level, and then it has JTAG on top of that. So it actually does JTAG over USB, and I don't understand how that works exactly. But this JTAG, the way I'm presenting it, is assuming you've got just a direct JTAG connection. And people still do that. Usually with this, there's a ribbon cable. There's a little tiny ribbon cable with like six wires, little tiny. You plug that in and you can get JTAG control. But of course, you can also run it on top of USB, which is how you do it for phones. Like if you're doing the Android debugger for an Android phone, and I think iOS probably does the same way. I've never done it with iOS, but and then of course the FPGAs. Make sense? Okay. And in the chip, by the way, that controls this on the FPGA boards is the USB blaster. And by the way, that was also the thing that we had trouble with in the class. Linux changed their USB subsystem and it stopped working with the USB blaster. But we fixed that by using the updated JTAG daemon. Okay, any questions? Okay, that was interfacing, and then I really blew through the FPGA, the system Verilog stuff pretty quickly because this is the first semester where it's required for you to have taken 611. So that's the reason I think I'll end up in subsequent semesters, I'll probably scale this down more and just make it a review of System Verilog. But if you forget your System Verilog from 611, you're going to want to review this stuff. So I talked about modules, structural, behavioral code. These are actually slides I got from my 611 lecture for the most part. We talked about syntax, numbers, the always statement, and we talked about various ways to build sequential logic. This stuff is important for you guys because in this class we want to be able to create a IP block that talks to the CPU. We're using the Avalon bus, and bus communication is done with state machines. I just wrote I had to write a question for the 611 PhD qualifier exam last weekend. And the question I came up with was an SPI. I asked the students to design an SPI bridge in Verilog. So you had a simplified interface on one side, and then on the other side it was SPI. And then you have to design a state machine, sequential logic to go through the sequence of things that have to happen for an SPI transaction, or actually just an exchange in that case. So you can see why you'd have to design sequential logic is if you want to build an SPI bridge. In fact, I was going to use that as a lab in this class, but I found out that if you go to Platform Designer, the Quartus Platform Designer, they already have that. I was going to have there to be an Avalon to SPI bridge. So you do an Avalon on one side and it spits out SPI on the other side, but it's already in there. You just drag and drop it and you got it, unfortunately. So that's why we do PWM, because they don't have a PWM module in there as far as I know. Okay, so then precedence, bit manipulations, combinational logic using always, blocking versus non-blocking. Does everyone remember this stuff? So yeah, blocking is, non-blocking is when you use the less than equal inside the always, and this does not enforce data dependencies, right? So in this case, N1 gets D, Q gets N1, but this N1 is the original N1, not the new one, right? Whereas over here with the blocking, it'll actually see the updated N1, right? That can get really confusing. You might say, what's confusing about that? It's just a data dependency. Well, in this case, it's pretty clear what's going on, but you have to keep in mind that this blocking and non-blocking is actually relative not to the inside of one module, but to the actual event, right? So in this case, the pause edge clock. So you can actually have multiple multiple always statements. And as long as they're sensitive to the same instigating event, the clock, you can get confusion if you use blocking versus non-blocking in there. And I've actually had bugs in my code, and I think in some students' code too, that took me a really long time to figure out because we couldn't explain what we were seeing in the waveform window. It didn't make any sense. It wasn't acting the way it was supposed to, and it was because they had blocking and sequential logic, right? So make sure you use non-blocking when you have sequential logic, clock logic, and blocking and combination logic, and you should be fine. Now you might say, why don't they just force you to do that? Well, I think there are cases if you're an advanced system Verilog designer, there are cases where you would want to use blocking and sequential logic, right? But I think we don't want to do that in this class. You can get yourself in trouble if you do that, right? Unless you know what you're doing. So it's better just to use this convention. By the way, in VHDL, if you guys ever look at VHDL, in VHDL, the way they implement this is instead of an always, they have something called a process. It's analogous to the always. It's a VHDL process. Same idea, has a sensitivity list and has the same, you can use if statements and loops and that kind of stuff, case statements. So it's kind of the same idea. However, instead of blocking versus non-blocking, in VHDL, inside of a process, you can create a variable as opposed to a signal. So these are signals. These are actual wires. So when you synthesize this N1 will be a wire on the FPGA. It'll be assigned a wire, right? But in VHDL, you can actually have a variable defined inside of a process, which then behaves like you're doing blocking assignments on it. So in case you guys ever look at VHDL and you wonder what the difference is between a signal and a wire, that's the difference. It's basically the same as the blocking versus non-blocking, right? Okay, then we talked about registers, parameters, FPGAs. Oh, did I ever cover this? I don't know if I ever got to this. Oh, I think I skipped this, didn't I? Okay, so this was not something I'm going to have on the exam. This was something that was designed to help you debug your projects. I don't know if you'll ever need it, but you can actually put in your design ports that allow you to send data into those ports from Quartus. And you can also put other ones where you can read from. So these are like virtual I/O pins, basically, that you can access through JTAG. And they're called the sources and probes. And so you can set up this, it's actually, this alt source probe it looks like a module name, right? It's used like it's a module name. And it is, except it's not a module that you create or that you even include in your code. It's a primitive. Some modules are primitives. They're actually mapped to physical hardware on the FPGA, like a LUT. You can actually instance a LUT. And that LUT, I don't know, it's got a special name. I don't know what the name of it. It's like alt LUT or something, alt LUT 6 or something. But that will actually create a module, but instead of having it as a module, you're actually referring specifically to the physical LUT primitive on the FPGA fabric. And the same thing goes for RAMs and DSP blocks and I/O buffers. But in this case, we're also doing this alt source probe is a physical piece of hardware. And then it's really easy to use, actually. It looks a little confusing here, but really all it is you just have you just give it a name and then you connect the inputs and outputs. And you don't have to use both. You can just use the inputs or the outputs. And then you can go, once you've got those in there, you can go into the sources and probes editor in Quartus and be able to send and receive data from your design when it's on the FPGA. The only problem is it's slow. It's not fast. It's designed to be, to be at the speed that you actually type in values. So you can script it in Tickle, which I had a PhD, actually Rasha did that in her dissertation. She did this thing where she actually generated a clock signal by writing a Tickle script that set one of these probes, or actually sources, high, low, high, low, high, low. But it was really slow. It wasn't really practical. And that's what the interface looks like, So in case it's not hard to figure out. And then there's signal tap. Did you guys ever use signal tap? Signal tap is a little bit higher speed technique where you can probe signals in signal tap, and they're actually captured once per clock, but only after the trigger condition happens. So they're more like an oscilloscope or actually a logic analyzer. So it works over JTAG, and this allows you to debug your design on the FPGA. Okay, and then finally, one last thing I want to mention is, because this is relevant for Lab 3, one of the craziest things in Verilog that everyone hates is this notion that they have two different types of signals. Now, in Verilog, there's multiple data types. They have like integer data type, like Java. They have traditional data types. But those are usually for non-synthesizable code like test benches, right? When you're designing synthesizable codes, you're only generally going to use a signal like a logic, right? And we use logic in System Verilog. But in Verilog, they don't have logic. It's split between two types, wire and reg. And they're both the same thing. They're both a signal. And they correspond to wires on the FPGA. The only difference is that you declare something as a wire if it's going to be driven by structural Verilog, like another module that you've instanced and you connect it to an output port, or an assign statement, and use a reg for anything that's driven by an always statement, which is absurd because a lot of times you don't know, when you're setting up your module, declaring your signals, you don't know what it's going to be driven by. You may change your mind, right? And inevitably you'll get an error if that happens. So it's not a big deal, but you're constantly having to change the declarations of these signals. It's something, obviously people recognize that this was ridiculous, so they fixed it in System Verilog. But if you write in original Verilog, you still have to deal with that. And unfortunately for Lab 4. Wait, what are we on? We're on Lab 3, sorry. In Lab 3, you have to design the Avalon IP, and you have to use regular Verilog for that. So that's something you should be aware of. Make sense? I don't know what the rationale is for that. It's some kind of historical thing. Okay, so any questions? Okay, so make sure, like I said, yes?
So I was going to wonder, is this slide going to be posted anywhere on the Dropbox?
These slides?
Yeah, for just Verilog video.
Yes, yeah, they should be.
Yeah, I was just looking and I only see there's only 4 slides and they're all it's control theory, Avon bus, the introduction.
Double check here. Why is that not? There it is. It looks like it's. Yeah, it looks like I've got it there. Are you clicking on the?
I was just looking at the schedule.
So if you go to this, go to the schedule and, sorry, wrong class.
Still wrong class.
Oh, sorry, you're right. There we go, 491. If you go under Avalon, oh, you're right, FPGA, oh, you're right. Okay, so this is just a platform slides, right? Yeah. Okay, yeah, you're right. Okay, I'll add those. Yeah, I forgot I had 2 different lectures for, I had one for just the FPGA practical stuff and one for System Verilog. I'll add those. Okay, thank you. If you don't see them soon, just send me an email to remind me, but I'll do that when I get back. Okay. Okay, any questions about that stuff? So the exam will cover that stuff, and the questions will be similar to the ones on the quizzes, so you can review the quizzes. If you have any questions, let me know. Okay, so I'm going to move on to the next topic. So at this point, you guys have everything you need for all the lab up through Lab 4. Oh no, actually no. I'm sorry. There's some stuff in this lecture that'll be relevant to Lab 4 too. But for the rest of the class, I'm going to cover kind of a miscellaneous topics. So I'm going to start with control theory. I just want to give an introduction to control theory. There are whole classes taught on this. In electrical engineering, it's Electrical 331. And they have one in mechanical engineering called controls. And so this is a huge topic. I just want to give you an introduction because And actually, you could argue, well, this is not really, and this is outside the scope of computer engineering because this is something for electrical engineers and mechanical engineers. That's true, generally speaking, but this class is on cyber physical systems and doing real-time control with embedded systems. And generally speaking, when you're doing that, you're doing control theory. You're trying to control something. And that's what cyber physical systems are, is when you have basically a computer controlling the physical world somehow, where it uses sensors and actuators, right? So any kind of robotics that you do, at least at the low level, when you're physically controlling a robot, if you want it to balance or walk or manipulate an arm, if you want to fly a drone, you want to have a drone that flies itself. That's all requires control theory. So I just want to give a really brief overview, just so you know enough to. In lab 4, we're going to implement a simple control scheme. In fact, you guys have already seen this a little bit in robotics. When you took 274, you guys did a PID controller. So this is very similar. I want to give a little bit more of a theoretical introduction to it. I think you guys, with a PID controller, how long did you spend on that in robotics? Did you spend a long time, or they just cover it briefly?
They touched on it, and they said, go build one, and then we got to struggle through building one.
Okay, okay. Well, so I'm gonna talk a little bit about that, and like I said, some more of the underlying theory. Okay, so control theory is about controlling something. They call the thing you're controlling the plant, because originally it was designed for plants. I think control theory, I don't know if it got its start in plants, like industrial plants, manufacturing plants, or if it got started with autopilots for ships. Ships and airplanes, the autopilot, that was I think that was another really, that's where the PID controller was developed. It was designed to, design an autopilot, I think for ships originally, and then for airplanes. But basically, you have a controller, and it's controlling some plant. And you're hoping that you can control the plant even when there's disturbances, like there's outside factors that affect the behavior of the plant. So, for example, if the plant is a car, like a Tesla, the disturbances could be like you have to be able to control it even, when it has to drive through windy roads. Or if it's like a drone, you want to be able to control it even if it's being blown around by the wind, that kind of stuff. So you want the controller to be robust to disturbances. And then there's the controller that most of us have experience with, the controller scheme that most of us have experience with is an open loop controller, where you basically give an instruction to a controller and then it sends an instruction to the plant, and then that's it. So, like for example, toasters work this way. You dial in your setting on your toaster, so you say, and the setting is intended to convey how brown you want your toast to be. So you tell your toaster, I want 50% brown toast. So if it has a setting from like 1 to 4, you set it to 2, right? And then you push the toaster down, and it adjusts the cooking time based on your setting. But the toaster never verifies how the toast is actually going to look. So I don't know if you have this experience, but most of the time it comes out and you're not satisfied with the color of the toast, right? Same thing happens with dryers. So you tell the dryer, I want dry, obviously the controlled setting there is I want dry clothes, and the dryer dries the clothes, but it never really checks to see how dry the clothes are in there. So it just assumes that if it runs for a certain amount of time, it'll reach a certain amount of dryness, but a lot of times you take the clothes out of the dryer and they're still wet, right? So if only there was just a moisture sensor in there that could check that and keep drying if they're still wet. But usually they don't have that. So if you did have that, like in the case of a toaster, if you could put like an optical sensor inside the toaster that would be able to measure the brownness of the toast, and then you could use that to determine how long you want to cook the toast, right? So this would be a closed loop system where you have the controller, so you have a set point, which is how brown you want the toast. The controller sends instructions to the toaster, which is how long you want to cook or maybe the temperature. And then the optical sensor will feed back the toast color, And it'll take the difference between what you want the toast color to be and what the toast color actually is, which is the error value. And the error value will be used to instruct the controller on what to do, right? So this is a closed loop system, and this is how toasters should work. Because that way, when you dial up a specific color, you're guaranteed to get that color out. It would use a closed loop controller. But no one's figured this is evidently impossible somehow. But in this case, the controller, the plant would be the toaster. So in a closed loop controller, the controller is sending manipulated variables to the plant. And the plant, it's reading back process variables. So the toast color would be a process variable, and the manipulated variable would be the temperature and the time that you're toasting the bread for, right? And then there's disturbances, and in this case, the disturbance would be like the ambient temperature of the room, right? Or the kind of bread, right? Because some bread toasts faster than other, wheat bread and white bread toast differently, right? So that would be considered a disturbance, and you would hope that the controller would be robust against the disturbances. You'd be able to get the desired brownness of your toast regardless of the ambient temperature of the room and the type of bread you put in. Okay, so you see these kind of control systems in self-driving cars, cameras do this when they focus, the autofocus. They have to adjust the focus and dial in that focus to achieve usually with a camera, you can't have everything in focus because you have limited depth of field. So you choose what you want to focus on, and the camera uses a closed-loop controller to actually focus on that thing. And then, and of course, in the case of a camera, the manipulated variable is turning the focus, and the process variable is read through. Different cameras have different technologies. They either use contrast detect autofocus or phase detect autofocus, but they have different ways to read the focus. And then the thermostat is actually running your AC, but it also uses a thermometer to measure the temperature, which is the process variable. And the drones use GPS, and some of them use inertial, like an inertial sensor, accelerometer and gyroscope. Years ago, I had an undergrad. We were doing a project. We wanted to build a drone. This was before drones became really common. We bought a helicopter that was remote controlled, and we took the radio receiver out of it, and we wanted to replace that with an autonomous flying system. And we had an accelerometer, a 3-axis accelerometer, and we wanted it to use dead reckoning, to be able to fly. We never got it to work because of the error in the accelerometer. You'd have to integrate the acceleration twice to get to position, and if there was any error in there, that integration would blow up the error. So we never got that to work. It was just not accurate enough. That's how the Nintendo Wii used controllers that use that technique too, and those were kind of unreliable too. So I think drones, they probably use if you're outside you can use GPS, but then I think they also might use a radio altimeter or other sensors to read the manipulated the process variables. Okay, but anyway, when you control a system. You have to understand, or when you control a plant, I should say, you have to understand the dynamics of the plant, the behavior of the plant. And this is where things get really hard with control theory, because you can design controllers. Control theory is a very well-developed field for plants that exhibit linear behavior, right? But nothing in the world is really linear. So at best, a lot of times you assume the thing that you're designing the controller for, the plant you're designing the controller for, is a linear system, and then you hope that the non-linearities in there don't cause you problems, and it'll still work. It'll still let the controller be robust. Now there are nonlinear control methods out there, but a lot of times it's you're doing some kind of a stochastic algorithm, or you're kind of trying to tune or optimize or follow a gradient for those. The really well-developed theory has to do with linear systems. And what do I mean by that? Well, when I say linear, you might be thinking like a linear equation, right? Where you have variables and there's a coefficient, and coefficient multiplied against each variable. It's a linear system, right? Linear equation. But what we're talking about here are linear time invariant systems, which is basically the linear version of a differential equation. So the idea is that you have you're using a differential equation to describe the plant, and when you have a linear differential equation, it means that you can multiply each state term, which is the signal, like a time series signal, right? Or any of the derivatives of that time series signal, or any of the integrals of that time series signal, they can be multiplied by a coefficient, right? So it's not the same thing as a linear equation. It's a linear differential equation, meaning that you have the variables are actually a time series value or the derivative of a time series value or the integral of a time series value, and you can multiply that by a coefficient. But you can't multiply the variables together and you can't square the variables, right? You can't raise them to a power. Does it make sense? So you're not seeing straight lines with a linear differential equation. You still see curved lines, right? But the differential equation, the ordinary differential equation, is linear. Okay, so that's called a linear time invariant system, or an LTI. And so they're used to approximate physical plants, right? Because, like I said, nothing in real life is strictly linear. Okay, so a linear time invariant system is called that because, as I mentioned, no state terms. The state terms would just be the variables, the time series variables, like temperature versus time. Those can't be multiplied by one another or themselves. And so that's the linear part. And the time invariant means that the coefficients don't change with time. The coefficients are constant, right? And so that means that an LTI has a frequency response, which allows you to change the phase and amplitude of a signal, but not changing its frequency, right? If you've heard of that. And so the LTI is something that might look like this. So you have, in this case, there's two state variables. There's u and y. And you can see here we have the derivative of y relative to t and the integral of y relative to t, right? So this is an LTI, but it's just an equation. It's just defining the relationship between these state variables. That's it, right? It's just a mathematical equation. But when you want to conceptualize this if you want to then assign these variables to being either dependent or independent, in other words, inputs or outputs in a system, right? Because like whenever we use an LTI to describe a plant, you're assuming that you've got an input and an output, right? There's no inputs or outputs here. This is just an equation. But it's you as the person that's using this to model a plant that has to assign each of these as an input or an output, right? So when you do that, the way generally that that's done, there's actually two ways to do that. You can do it with a state space equation or with a Laplace equation. So I'm going to first cover the Laplace way to do this. So if you take the ordinary differential equation and you take the Laplace transform, basically you're going from time domain to frequency domain, so t domain to s domain. And so in that case, anytime you have a derivative of a state variable like y, you just multiply it by s. And whenever you have an integral, you multiply it by s raised to the power of the degree of the derivative, right? In this case, it's the first derivative, so I multiply it by s. If it was a second derivative, it would be multiplied by s squared. And then for the integral, you multiply by s to the negative 1 for degree 1 first integral and s minus 2 for second integral. So and then the state variables are usually shown as capital letters by convention. So notice there's lowercase y here and uppercase y here, and then this is y of t over here, and this is y of s here, right? So you basically, once you do the Laplace transform, you get this. And then when you decide what are your inputs and what are your output variables, you have to take this S domain expression and you want to represent it as a ratio of the output divided by the input. So if my output is y of s, you think of that as your dependent variable here, and u is your input. That's kind of your independent variable. You want to rewrite this as a ratio of y of s over u of s, right? So in this case, to do that, you have to use algebra. You got to use a lot of just basic algebra here. You factor out y of s here, and then you divide, both sides of the equation by y of s, and that gets you a form which is y of s over u of s is 1. Oh, I'm sorry. Actually, I always get these switched. Y is the numerator, because that's the input, and u is the denominator. So you have to divide both sides of the equation actually by 1 plus s minus 6s to the negative first power. So you end up with 1 over 1 plus s minus 6x to the negative 1, right? Okay, does it make sense? So this becomes this is called a transfer function. All right, so you start out with a basic equation. So if you guys have probably done this in circuits too, right? So you can do this for a circuit, an RLC circuit, or you can do this for a physics. Newton's laws can be used to construct this type of equation. Just Newton's laws for physics, basic physics equation. But generally, when you do that, it's just an equation. It's just the relationship between these variables. When you make this into a transfer function, that's when you are conceptualizing this equation as a transfer function, which implies that you have an input and an output. Does it make sense? In this case, there's just a single input and a single output. And if you do it like this, you're limited. If you put it in this form, you're limited to one input, one output. If you need more than one input and more than one output, you have to use a matrix form of this. You have to go to linear. You have to combine linear algebra with Laplace together. But in this case, we just have one input, one output. Okay, single input, single output, SISO. Okay, so now you might say, well, what's the point of all that? The nice thing about these transfer functions is they're composable. So if you have a transfer function, so this ends up becoming like a block diagram editor, like in a CAD tool, where you can take a transfer function and you can have it, you can connect them. You can connect them together like building blocks. Okay, so you could take one transfer function and another, and you can feed the output of one into the input of the other. And when you do that, you get a new transfer function that is simply just the product of those two. You just multiply them together, which is really convenient, right? You multiply them is when you connect them in series. Okay, so in this case, this is y over u. So y is the output, u is the input. And this one is g over y. G is the output, y is the input. So this is y over u, this is g over y. And so you can multiply these and get g over u, right? Because you're chaining them together. What ends up happening is that this y of s it disappears. Because here it's in this numerator here and denominator here, right? So the y of s disappears, and you compose this as one block. You can merge them together. Mathematically, all you have to do is multiply the transfer functions to do that. Does it make sense? And that's called the convolution. When you multiply S-domain functions, it's called a convolution. I don't know why it's called that. Okay, does that all make sense? Okay, so the other thing you have to understand, the last concept here is stability. So I mentioned that an LTI can change, the transfer function is really what that's doing is it allows you to change the phase and the amplitude of a sinusoid, of a signal that you send in. However, there are cases where you put a signal in and you can put a constant signal in, a bounded signal. When I say bounded, a finite signal is what I should say. A signal that's finite. You put it into a transfer function, and the transfer function causes that signal to blow up, get bigger and bigger and bigger forever, right? That's called an unstable system. And so now you might say, well, wait a minute. I mean, if you're modeling a physical thing as an LTI, you're telling me that there's a physical phenomenon where a device, for example, can blow up a signal infinitely. That doesn't seem like that makes any sense. And generally, it's not the case for physical systems. And the reason for that is because there are damping factors involved. And I'll show an example of this. However, when you combine two LTIs together to create a controller, so basically what we're doing here is that we're modeling the physical thing as an LTI and the controller as an LTI, and we're going to sandwich them together, right? That's kind of the idea. When you do that, it's possible that the controller, in combination with the plant, becomes unstable and blows up, right? So there's really two objectives for designing a controller. One is to have it successfully control the plant. So you put a desired set point in, and the plant will, bend to your will, right? And you can manipulate the plant to do what you want it to do, right? In a reasonable amount of time, right? That's one objective. The other objective is you want to make sure that the resulting system is stable. The plant and the controller together have to be stable, right? So you want it's called bounded input, bounded output stability. If you give it a bounded input, then it should have a bounded output. Make sense? Okay. All right. So there's three ways I know of to actually detect whether you have a stable system. The one that's really common is to calculate the impulse response. So the idea with that is that if a system is unstable, it's usually only unstable at certain frequencies. And those frequencies are usually the natural frequency or the resonant frequency of the system. But you don't really know, you may not know what that is. You might not know what that is, depending on how much information you have about it. If you have the transfer function, you can actually find the resonant frequency. You can calculate the natural frequency. But one way to check for stability is to hit the system with an impulse on the input. An impulse is an input of 1 at time 0 and 0 everywhere else. So it's literally an impulse. It's almost like you take something and you whack it with a hammer, essentially, is what you're doing. And what that does is that injects an infinite number of sinusoids, because in order to generate an impulse, you have to add together an infinite number of sinusoids together to generate that impulse. So basically what you're doing with an impulse response is you're hitting it with every possible frequency. So you think of like a tuning fork, has a resonant frequency, and the way that you get a tuning fork to oscillate at that frequency is you whack it. That whacking of it puts an impulse into it, and it excites the resonant frequency, which is that one tone the tuning fork will give you, right? That's the impulse. It's basically, like I said, it's basically hitting something with a hammer, essentially. But mathematically, it's significant because that impulse, again, the impulse is defined as 1 at time 0 and 0 everywhere else. So it's an infinitely small pulse, essentially. That has a Laplace transform of 1, right? So the Laplace transform of the impulse is 1, right? The Laplace transform of other types of inputs, like a step response, like a step is where you start out at 0 and you go to 1 with a step, right? That has a Laplace transform, I think, of 1 over s, right? But the impulse is a very simple Laplace transform of just 1, constant 1. So that's why it's a common way to test these things. The other approach to determining if a system is stable is you find the poles. The poles are the values of s that make the transfer function undefined. Right? And what I mean by that is if we go back and I show you that example I had, this example, right? There is a value of s here that will cause the denominator to be 0. That'll cause a divide by 0, right? And in this case, there's actually 2 values of s because it's a second degree polynomial. Those values of s are called the poles. And that, if those poles, by the way, s is a complex number, right? So if you take those poles as complex numbers and you plot them on a plot where the x-axis is the real component and the y-axis is the imaginary component, if those poles are all located on the right-hand side of the plot, meaning that the real component is negative. As long as the real, it doesn't matter what the imaginary component is, but if the real component is negative on all the poles, then it's stable. And I'll show an example of that here in a minute. And then finally, the other thing you can do is you can simulate. You can simulate the system with a step. You just run a simulator. So what's the simulator everyone uses for this? Anyone know? Well, you know, everyone always says anything you can do in MATLAB, you can do in Python, right? But this is the one thing Python I don't think can do. MATLAB has this thing called Simulink in it, which it allows you to actually take transfer functions like that and you can simulate them. It has an integrator built in, a solver. There might be a way to do it in Python. I've never seen it. But it's the one thing that kind of MATLAB has basically a monopoly on, sort of. MATLAB and Simulink. I think there's some other tools that are up and coming. There's one called OpenModelica. But basically, most people use MATLAB for this. And so MATLAB has a simulation engine in it, much like we use like QuestaSim for simulating System Verilog. You can simulate these things. And so you can simulate and see if it blows up. Okay, so let me talk a little bit more. So this is the step. This is called the, by the way, the impulse. Sorry, not the step, the impulse. The impulse is called the Dirac delta. The Dirac delta. I don't know why it's called that, but it's basically, it's a value, it's a function that's 1 at times at 0 and 0 everywhere else, right? And as I mentioned, that the S-domain representation of that is a 1. And then there's a step function, which is where, this is a step function where anything, it's 0 at any negative input and it's 1 everywhere else. So it's a step, right? But the step function is good too because the step function also contains all the frequencies, all the sinusoids. However, it's a little bit more complicated than the impulse because it requires it has its own transfer function of 1 over s. So a lot of people just use the impulse instead of the step. But I think they're equivalent for determining stability, right? Okay, so let's take a look at that example I had before. So here's a transfer function, which is, again, y is the output, u is the input. So y is the numerator, u is the denominator. They're both in the S-domain. So we end up with this, basically this ratio. The ratio is between two polynomials defined for s, over s, right? In this case, it's 1 over 1 plus s minus 6s to the negative first. Generally, you want to have these polynomials in regular polynomial form. So you want the polynomials to be comprised of powers of s that are positive or 0, right? We don't want to have a negative exponent here, right? So to solve that, you can just multiply this by s over s, right? So then you end up with s over s plus s squared minus 6, and then you want to rearrange this polynomial to be in order of exponent. So the s squared should be first, the s should be second, and the minus 6 should be last, right? Okay, so then, so you put it in that form. Okay, so then you can say, you can factor the denominator, and this is just s plus 3 times s minus 2. And after we factor this, we know that the roots, the zeros, or the poles, the values of s that'll give you a 0, and thus, that give you a 0 for the denominator, and thus give you a divide by 0, is going to be s is minus 3 and s is 2, right? Now you can also use just the quadratic equation to get this too, but in this case I was able to factor it, right? So that gives me two poles. One pole is over here on the right-hand side of this plane, right? And one's on the left. So both have imaginary component 0, right? But that's not always the case. I mean, you can imagine it's not too hard to find a polynomial that has imaginary roots. It's pretty common. I just chose one where there's no it's just the real. The roots are just real, just to make it real simple. So both of these poles are on the real axis. One of them has a negative real and one's a positive real. So this is an unstable transfer function. This transfer function will blow up with certain inputs, right? Certain frequency inputs. So that's unstable. Now, one way, now here's the problem. How do you know? Like, how do you see it blow up? Well, this is the problem because this is actually kind of difficult. You know it's unstable, but what if you want to actually see what happens? You want to actually see what happens, like you want to see the impulse response. What does the impulse response look like? Because it's unstable, because it has a positive or zero pull, or sorry, it is a pull with a positive or zero real component, I should say, right? Because of that, it's unstable, so I expect if I hit this with an impulse, it's going to blow up, right? But how do I see that happen? Where does that happen? How do I observe that? Well, you could simulate this in Simulink. You can build a Simulink design and hit go, and it'll show you. Or you can figure it out by calculating the inverse Laplace transform, right? Get it back into the time domain, right? And then you just do a regular plot in the time domain. Then you can see what happens in the time domain, right? So how does that work? Is it possible to do an inverse Laplace transform? Kind of. The problem is that generally the way you do that is you look at a table. You look at a table for this. And you try to get this equation into the form that fits the table. So in the table, there's one entry in the inverse Laplace transform that says 1 over s minus a has a time domain representation of e to the at. It's an exponential function. So in order to do the inverse Laplace transform, we have to get this into that form. That makes sense? We can't do it directly. There's no way to do it. But if we can do it, if we can do this, it'll give us a closed form solution. So we don't have to. So by the way, let me step back here. When I say simulate, by the way, the simulation is actually is a numerical solving. So what you're doing is it's running an algorithm on this thing, on this transfer function, to basically, number one, it has to discretize it. So you have to basically sample at fixed points in time. That's number one. And two, it's using a numerical algorithm, it's using a numerical method to figure out what the response is to this. It doesn't solve it directly. It does a numerical solution. In other words, it approximates it using an algorithm, right? If you do an inverse Laplace transform, you're actually solving a closed form of it. You're actually converting this to another equation that you can plot an equation easy, right? But you can't always do that inverse Laplace transform. You can do it in this simple case. As long as I could do some algebra to get it in this form into that form, right? Then you can calculate a closed form time domain representation of this S domain thing, right? So how do you do that? You guys probably remember this from high school. This is a trick you can do. So what we really want to do is we want to take this and convert it into a form that's a sum of A over S plus something, B over S plus something. Because that way, each one of these sub-expressions then matches up to this table entry, right? So how do you do that? How do you go from that form to that form? Well, you can see in this case, I took the denominator here and I broke it up into, instead of having the denominator be a product of these two sub-expressions, I broke it up into S plus 3 and S minus 2, right? And then I have to figure out just what A and B are here. Does that make sense? Okay. So how do you do that? Okay, so one way to do this doesn't always work, by the way, because the problem is, I mean, you might be thinking to yourself, okay, the fundamental issue is you have one equation and two unknowns here, right? You have A and B are unknowns. If you want to solve for two unknowns, you have to have two equations, right? But we only have one equation. So this is an underdetermined system, so we got an issue. There is a little bit of a workaround to this, though. The workaround is you take this and you rewrite this as, so you take this and you rewrite this as A times S minus 2 plus B times S plus 3. In other words, what you're doing here is you're multiplying this thing by S over 2 over S over 2 and S plus 3 over S plus 3, right? and you get this expression, right? Makes sense? So these are equivalent, right? Okay, and then you say, okay, well now if you have it in this form, you can cancel out the common denominators here. So you have s equals a times s minus 2 plus b times s plus 3. Okay, now the issue here is we still just have one equation and two unknowns. Okay, but because it's in this specific form, we have a workaround where we can actually knock out one of these unknowns if we assume that s is, say, 2. If s equals 2, then you'll have 2 minus 2 is 0, and that a actually will disappear, and we'll just be left with b, which is one equation and one unknown. Likewise, if we set s to be negative 3, it'll set this sub-expression to 0, and it'll knock out 2, right? So basically, we can solve this in the case where s is 3 and when s is when s is 2 and when s is negative 3. So let's set s equal 2, which will destroy this a term, right? And so then we'll have 2 equals b times 2 plus 3, 5b, right? So then we can solve for b. And then we can do the same thing. We can set s to be negative 3. And by doing that, we knock out this b term, and we're left with just the a term, and then we can solve for a. Make sense? And so we end up with a. We can then solve for a and b. A is 3/5 and b is 2/5, right? Now, by the way, this only works if a and b are unique values. If a and b are the same value, you can't use this approach. It makes it impossible to solve. So this is a very specific case where we can solve for a and b even though we only had one equation, right? But once you have this, then you have these two terms which you can take the inverse Laplace of both of these, right? Which basically gives you these two exponential functions in the time domain where you just take you take the numerator, and that's kind of that goes in front of the exponential, and the a is the negation of the a becomes the exponent, right? So these are called eigenfunctions. So you end up with, you take the inverse Laplace transform, and you get 0.6 e to the negative 3t plus 0.4 e to the positive 2t, right? So this ends up being now here's where this is a little confusing. This is the time domain representation of the transfer function, right? The transfer function. So this is assuming that we have an input and an out. This is not the differential equation. This is the transfer function. So this is built in. What's already built into this inverse Laplace transform is our independent and dependent variable, right? But you might say, well, wait a minute. I only see one. I mean, you've got time, right? Well, okay, so this is actually ends up being, because it was the transfer function and it was just the raw transfer function, then what it really is the impulse response. Because remember I mentioned that transfer functions are composed by multiplying them, right? And I mentioned that the impulse response is a S domain of 1, right? So basically what we've done is we take this transfer function, we've multiplied it by 1 in the S domain, and then did the inverse Laplace. So this is the impulse response, right, in the time domain. So it's basically 0.6 e to the negative 3t and plus 0.4 e to the negative 2t. And then you can plot this relative to time, and you can see what happens. This is the response of the impulse. So the input here was an impulse, an input of 1 for time 0. And the response to that was a blow-up, an exponential blow-up, after 8 seconds. At around 8 seconds is when, or maybe 9 seconds is where you get the elbow of that curve where it shoots up. You know, where the slope, you have unity slope there, and it goes up. Unity slope, you know, where, you know, you have a 1 slope on the elbow there. Makes sense? So it took this guy, we gave it an impulse, in about 9 seconds it shoots up to infinity. Make sense? Okay, now I simulated this in Simulink, but for whatever reason I couldn't figure out how to do the impulse in Simulink. So I just did a step function instead, right? So this is the step response. And so you can see that in the step response is a little different from the impulse. You actually still get this blow up, but it's weird. The step response gives you this kind of oscillating before it blows up. But it still blows up. It gets bigger and bigger infinitely. Okay. In this case, I hit it with, instead of a step response or an impulse, I hit it with a sine wave. And I excited the resonant frequency. So the natural frequency, oh no, actually, no, I'm sorry, that's not the, is it? No, it's not the, I'm sorry, scratch that. That's not the natural frequency. But I hit it with a sinusoid that's 2 radians per second. That makes sense? You ever heard of radians per second? 1 radian per second is 1 over 2 pi hertz, right? Yeah. 1 hertz is 2 pi radians per second. So if you want to go from radians per second to hertz, you divide by 2 pi. If you want to go from hertz to radians per second, you multiply by 2 pi. So it's just another way of saying hertz, basically. So sine 2t, that's a frequency of 2 radians per second. So you just give it that, and you can see that, you can see the period is about, pi, see it stops here at about 3.14 here, right? So, so anyway, I hit it with this sinusoid, and you can see it blows up. But this is using a numerical solver in Simulink. Okay, so what happens then? Let's say we try this again. But this time, I just changed I just manipulated this to be s over s plus 3, s plus 2. I just changed it arbitrarily. Does it make sense? Just so I can make it stable, right? I think one of these was negative, right? That was the s minus 3. I just changed it to plus. So I made both of these guys plus because I wanted the roots to be negative, the poles to have a negative real component. So I just changed it, and then I applied the same technique. Now, obviously, in this case, the poles here are -3 and -2, you're right? And so both of these poles are negative real portion. The real portion is negative, which means they're in the left-hand plane, right, of this plot. And so this is a stable system. So I went through all the same steps I did before. I'm just going to skip ahead a little bit, and I got the eigenfunctions. The eigenfunctions in this case had different coefficients, and they both had negative exponents. And because if you have an exponential function with a negative exponent, then it's going to converge. It's not going to blow up. And so the step response for this guy, this one's pretty wild, actually, when you look at it. This is the step response I got from plotting the eigenfunction. It goes up high to 1, and then it comes down past 0, goes under 0, and then it stabilizes around 0. Right? So I went and I ran that in models in Simulink. So in Simulink, again, I can't figure out how to do an impulse response. I know you can do it. I just didn't know how to do it. So I did the step response, and you can see the step response has that same kind of behavior as I had with the impulse. It kind of shoots up, and then it comes down and settles. Right? So that's stable. And then I hit it with a sine wave, and you can see it changes the amplitude of that sine wave. You can see from the vertical axis that it applied a filter on this. It attenuated this, and it kind of changed the phase a little. Maybe not, a little bit, right? But it changed the amplitude, right? And it's stable, right? Okay, any questions about that? I'm just about out of time. So just to kind of summarize that real quick, we talked about transfer functions and how to write a transfer function in the S domain and how to determine if it's stable. Now, I mentioned to you guys that a real system will be stable in general. Like if you have I'll show some examples of that. If you have a spring or a circuit, an RLC circuit, you're not going to have an RLC circuit that you hit with a sine wave and it ends up generating an infinite amount of energy inside it, right? That's not going to happen. The reason for that is the resistance in there. It provides a damping effect, right? The spring is the same way. If you have a spring and you hit it with its natural frequency, it'll eventually stop getting, bigger and bigger. Tuning fork is the same thing too. When you whack a tuning fork, you'll excite its natural frequency, but eventually it'll kind of fade away. That's because energy is being dampened, converted to heat inside that tuning fork, and eventually it goes away. That's why, there's a damping effect. But like I said, because you can take a controller and combine it with a plant, and that creates a new transfer function, that transfer function could become unstable. In other words, if you screw up your controller design, you can end up with an unstable system. Now again, there's limits. What your controller will do is keep going bigger. It'll keep driving the plant with bigger and bigger manipulated variable values, but eventually it's going to saturate at some point. It's going to hit a limit, right? So even then, you're not going to see an infinite explosion, right? You're going to hit some kind of limit because real controllers are nonlinear, and we're imagining everything in this case as a linear system. So in a purely linear system, you would get this infinite growth in an unstable system, but in practice you can't, right? Does that make sense? But you still have to make sure your controller and plant combo are stable. Okay? Okay, great. We have spring break this week? Fall break, yes. And then I have a quiz online. It's due not this Friday, next Friday, covering the control theory. I was planning to lecture on Tuesday. Right, is that okay with you guys? Because your exam will also be next week. And if it were an in-class exam, you'd just be taking the exam. But I'll just give a lecture, finish this lecture, and then maybe we can do an extra lab class. Is that all right? So in other words, you're going to have lab next week, a lecture, and you have to do your exam. Is that okay? Okay, but this week you got fall break. Okay, thank you.